for the kind introduction. So I need to know who the audience are. Who among you describe yourself as HEP-TH? Very good. As a quantum information? No? Condensed matter? Condensed matter? HEP-PH. Okay, GRQC. Very good. So it's rather broad audience, but theory. So Sakura instructed me. Oh, lattice. Excuse me. And so Sakura instructed me to give prepare my talk for broad audience, but also since we are all theorists, so it can be technical. So I hope I can hit the right balance. So I started with some general comments. So we all know that physical world is hierarchical. And Ken Wilson mathematically formulated this idea in the language of effective theory. So for each energy scale, there is a set of laws called effective theory that describe physical phenomena at that scale. And we can be ignorant of more fundamental law at higher energy. And for example, the pion theory is an effective theory of QCD. But we don't need to know detail of QCD to discuss pion physics at energy far below QCD scale. So basic assumption is that as long as the effective theory satisfies consistency conditions that are evident at applicable scale, then it can be derived from more fundamental and mathematically consistent theory at higher scale. So this is how the effective field theory idea operates. So in this talk, I'd like to show that this assumption is false with gravity. So that's what I would like to show. So of course, there are situations where even Einstein gravity can be described treated as the effective theory. And in fact, this morning we had a very interesting talk actually doing some useful calculation in that approach. And for example, many examples, Hawking radiation from black hole, the fluctuation of cosmic microwave background radiation, caused by quantum effect during the inflation. This is my favorite example. So you can calculate the Newton potential. This is what we learned in undergrad. And if you turn on, include special relativity effect, then there is a correction. There is a c square, g Newton, but not h bar. But then you can actually calculate the one loop correction. And there is actually a number associated with 41 over 10 pi square. This is for pure Einstein gravity in 4 dimensions. If you have matter, you get different number, but these are calculable. Well, there's a particular reason that this is calculable. These are coefficients of non-analytic term, but this is actually number. In principle, one can go and measure this in the laboratory, although, of course, there is a small number. This is a Planck's length square, so this is hard to do that, but in principle, it is measurable. So this leads to, since we are at KITP, so I thought I should quote from the Joe Poltinsky. So this is from his nice lecture note from Tassi Summer School, where he said, presumably no field theory we have ever encountered, and perhaps no field theory of any type is complete up to arbitrary high energy. They are all effective theory, valid up to some cutoff. So, however, the gravity is different, and there are reasons to believe that any quantum theory of gravity must be complete by itself. So this is a standard argument. Typically, when I give public lecture, I'll do that. But since this is broad audience, I just very briefly mention that. So with gravity, the separation of UV and IR scale fails. And for example, the radius of black hole horizon grows with energy. So that means that if you build a very powerful accelerator and collide particle and try to probe short distance, normally it goes like inverse of energy, the Compton wavelength. But there is another term here which grows like energy. And so that the minimum of this, the maximum of, minimum of this is bounded by, the maximum of this is bounded by this. And so we cannot probe distance shorter than this scale, and this is called Planck length. So this is related to the fact that with gravity, UV and IR degrees of freedom fail to decouple. So this calls into the question of the validity of the Wilsonian paradigm when gravity is included. There are more chairs down this way if you want to come. Qumran buffer actually proposed, based on this unknown string construction, that the proposed set of conjectures that there are conditions that any gravitational effective theory must satisfy, but which are not obvious from low energy consideration alone. And if such condition exists, then that would falsify the basic assumption about the Wilsonian paradigm. So what I would like to do today is to show a few concrete examples that actually happens. So we have proven some such condition for gravitational theory in negative cosmological constant by using ADS-CFT correspondence as a first principle. So this is actually proof in principle. This is not our word, but this shows that that there are conditions in gravitational theory that are not obvious from low energy point of view. And some conditions, not all, but some of the conditions I will mention, especially the latter one, if you let me get all the way to the end of my talk, I'll mention some examples where they are definitely counterexample to Wilsonian paradigm. You have a question?
I don't want to stop you from reaching the end of your talk, but
it's up to you. You can choose.
So when people use the term UV-IR decoupling or the lack thereof, could you be more specific? Because to me that always seems a little ambiguous. You're not saying that in order to make some IR prediction, you need to know the full UV.
What I mean is that the basic assumption, well, depending on how you interpret Wilson's idea, but one interpretation is that you can be ignorant about ultraviolet completion. That you can just write down any low energy effective theory that that looks consistent in that scale and hope that it can have a consistent completion in ultraviolet. And that's what I refer to in this particular context as a UV-IR decoupling, that I can be ignorant about what kind of theories are waiting for us in ultraviolet.
But you can still be ignorant and still have complete predictive power in the IR.
Right, but you may have a wrong prediction.
Oh, just in terms
you can be wrong prediction because the theories that you are looking at can be inconsistent.
Yeah.
Therefore, so there can be no theory which comes from you are looking at a theory which does not have you may be looking at a theory which do not have UV completion, does not have UV completion. Therefore, your prediction can be wrong.
It can, but it's still, the UV still decouples in the sense that your prediction will be independent of the UV.
Let me explain example so you know exactly what I mean by this.
But in this way you're implying that...
let me explain example so you know what I'm implying. Okay? Yeah, so ADS-CFT correspondence, I hope everybody have heard about it. So I'm going to use conformal field theory as a definition of quantum gravity theory and derive several non-Wilsonian conditions from consistency of conformal field theory. Okay? So there are actually two main threads of non-Wilsonian statement that I would like to tell you about. So there is one thread which goes from no absence of global symmetry to weak gravity conjecture, and then another is the absence of adjustable parameter and goes to distance conjecture. Okay, so let me start from the first example. First set of conditions. So absence of global symmetry, which is quantified by weak gravity conjecture. So this is actually perhaps the second oldest Swampland conditions that was proposed by John Wheeler and in the paper co-authored with Misner called Classical Physics as Geometry, 1957. And in the modern interpretation of this statement is that there is no global symmetry in quantum gravity. So we actually proved the absence of global symmetry in quantum gravity using the ADS-CFT correspondence. So I would like to sort of first summarize what we did. But before we do that, I thought it would be useful to give you some background information, especially explain what precisely I mean by global symmetry in quantum field theory, especially in conformal field theory, and global symmetry in quantum field theory, quantum gravity theory. And I would like to show you that using property of global symmetry in conformal field theory, number one, that I would like to show you that 2 is absent. Okay? Okay, now global symmetry in quantum field theory. So when we say that, so we are, here I'm only going to talk about invertible global symmetry. I briefly comment on non-invertible symmetry, but I restrict myself to invertible symmetry. And suppose you have a Cauchy surface sigma times time. We say that it has a quantum field theory on it has invertible global symmetry if these conditions are satisfied. Okay, so first is that there is a unitary homomorphism from group to the set of unitary operator on the Hilbert space. Now I call that as a homomorphism. It can be a representation, but I would like to extend a little bit so that what we're going to do is applicable to spontaneous symmetry, spontaneously broken symmetry. So relaxing the condition a little bit and include general homomorphism would be helpful. Now, I assume that this unitary operator acts locally. So that means that if you consider algebra of local operators, so suppose you consider any open set of the Cauchy surface and algebra of local operator on it, then it maps the algebra of local operator into itself. So that's part of the assumption that that is a reflection of locality of this operation. And I assume that this unitary operator represents a group faithfully on this set of local operators. Namely, the set of local operators is enough to understand what global symmetry is. And so, for example, you can postulate that any quantum field theory has monster symmetry that just acts trivially on the Hilbert space. So that won't be interesting. So I want to say that this unitary action is faithfully represented, and being conserved, it means being symmetry means that the corresponding operator is topological. So that means that it commutes with stress energy tensor. So these are conditions. Okay. Any questions? This obvious? Okay.
Probably the second property is more important because you can talk about algebra. You should talk about algebraic approach. And Hilbert space is not necessarily fixed.
Right. Yeah, it's algebra of operators that's more important. In fact, the language used here is going to be important for what I'm going to say in the following. I'm glad that Albert is here to keep an eye on what I'm going to say. So one of the important features of this kind of symmetry that I'm going to talk about is the splittability. So splittability is something that is actually obvious for continuous symmetry, because if G is a continuous, symmetry is a continuous, then Noether's theorem says that there is a Noether current. And then you can write this unitary operator as exponential of integral of Noether current for this element. So if that happens, then suppose, for example, so that means that you can define this operator not only on the entire Cauchy surface, but also on some open set, subset of Cauchy surface. And basically just restrict to this integral in that. And such operator would act just like this unitary operator for the algebra of operator in R, but commute with algebra of local operator in the interior of the complement of R. So that means that you consider complement of the subset in the Cauchy surface, and then consider largest open set that is contained in it. And so then, for example, if all these R's are disjoint on Cauchy surface, then obviously, if you write this operator as exponential of integral, then if you consider a disjoint union of such open set, it becomes product of operator associated to each open set. Okay, so this follows from this Noether current, but it was pointed out by Buchholz, Dopplischer, and Longo in 1986 that this actually property can also be extended. This is more general. It can be extended to even to discrete symmetry. You can define such local operation even for discrete symmetry, provided that quantum field theory has split property, which I will explain in the next page. So, well, So I'm actually going ahead of myself a little bit, but the important point I would like to make is that this means that global symmetry action cannot change the entanglement structure between different open regions in the Cauchy surface, because the action of symmetry operation on the Cauchy surface is a product of operator. So if you have different regions, suppose the different regions are entangled with each other, you act symmetry operator, but they're acting locally, so they cannot change the entanglement structure. Any entanglement measure will not be able to detect the action of symmetry operator, which will become important later in my talk. So, so there is actually another term that becoming popular, especially in the literature of Swampland, called endability. So I asked actually a couple of experts here this week whether the splittability I defined in this way is different from endability, and they both agree that actually, if you don't know this word, then you don't have to worry about it. But if you know this word, I would propose we are not going to use endability, because there is already this word called splittability used already 40 years ago, and I propose we shouldn't confuse by inventing new term for the concept that already exists.
Sorry. Endability usually refers to the charged object, not to the...
Sorry?
Endability usually...
We can discuss that. I think we had the long discussion with Jake and Xiaohen. Right. But you can comment on this if you want to. Yes, please.
Well, just wanted to ask that endability usually is a property of the charged operator, not of the charges. So what do you mean here?
So if you have such operator for open set, and then if R has a boundary, there appears some charged operator on the boundary. Jake has some comment.
Maybe it's worth saying that I think endable is a useful notion even for non-topological extended operators.
Yeah.
Okay. So that's what you mean. Then I agree with you. Okay. So yes, indeed. So if we want to use endability specifically for non-topological operator, I have no objection. But for topological operators, there is already established terminology. So that's all I want to say. Okay. So I said that for quantum field theory, for any quantum field theory with split property, this splittability is true. So I just need to specify what I mean by split property is. So suppose you have quantum field theory on Cauchy surface times time, and we say that it has split property. What we mean is that if you consider two open surfaces, one inside of the other, so let me draw some caricature. So here is S, and here is S prime, okay? So closure of S is in the interior of S prime. So then the splittability requires that in between the algebra of local operator in S and algebra of local operator in S prime, since S prime contains S, obviously the algebra of local operator of S prime can be larger than that of S. Then the claim is that there's actually a nice algebra in between called N. And this has a property called type 1 factor. So I need to explain the technical term here. So the factor means that for polynomial algebra, factor means that its center is just trivial. And it's called type 1. If it has a property that quantum field theory often take it for granted, that this action, this type 1 factor action, can be defined in such a way that Hilbert space actually decomposes into tensor product, and the type 1 factor can be realized as algebra on one factor, and the commutant is the other factor. So this is actually what we usually assume. For example, we talk about Ryu-Takayanagi formula, entanglement entropy for quantum field theory. We naively assume this, but that holds not for the large algebra of local operator, but something bigger. Okay? So that's something we need to be careful. And so when this happens, then we say that quantum field theory is split property. And we have to be careful because the algebra of local operator itself is not in general expected to be type 1 factor. It's something more nasty. So this is something that people like Araki clarify this. And but fortunately, for quantum field theory in Euclidean space or Euclidean space times that R times sphere, which are equivalent in the case of conformal field theory, then all theories are expected to be split. So we assume this is the case. So therefore, splittability holds. Okay? So that's what I wanted to say about the global symmetry in quantum field theory. Now, global symmetry in quantum gravity is something we need to define, but this is a little bit tricky task because I first need to define what it is, and then I need to demonstrate that it doesn't exist. So I need to define something which does not exist. So what I would like to do is list the kind of things we believe what we mean by global symmetry, and then I would like to show that that set of assumptions is inconsistent. That's what I would like to show. So the reasonable assumption is the following, that by requiring that global symmetry in the bulk of ADS is defined in such a way that it will reduce to the quantum field theory, that global symmetry in quantum field theory in the limit of vanishing Newton action, and with symmetry action on local operator in conformal field theory implied by that on the quasi-local operator with gauge and gravitational dressing in the bulk. So here is what I mean. So quasi-local operator means that so in the gravitational theory there is no strict notion of local operator as Ira was talking this morning, but you can add gravitational dressing. And then we can also allow some extended objects like black holes, for example. So those can also correspond to some local operator in conformal field theory, albeit with very large conformal dimensions. So we are considering all these quasi-local operators. And so then from that, it follows that if the quantum field theory, quantum gravity in isolated space has some global symmetry, it would imply that corresponding conformal field theory has to have also the global symmetry. But it's reasonable to assume introduce a few more notations. I already mentioned that if you have global symmetry in quantum gravity, it's reasonable to assume that it is also the global symmetry in conformal field theory. That was what I was arguing over here. But I would like to impose a few more conditions, and I hope you find them reasonable. If not, we can discuss. Okay, so one of the conditions is that it acts locally within quasi-local baroque operator, preserving their gravitational dressing. In particular, the claim I'm making here, the gravitational dressing would be neutral for the kind of global symmetry we are considering. Because, as Ira was demonstrating, gravitational dressing typically involves just calculating the geodesic distance. And so I'm assuming that this calculation of geodesic distance is invariant under global symmetry we're considering, and acts faithfully on gauge invariant quasi-local bulk operators. And so this is sort of taking analog of this notion of global symmetry that in the case of quantum field theory that it's faithfully represented by the local operator. So we require same kind of conditions for quantum gravity theory. And as act distinctly from asymptotic conformal field theory, we want to have what we may call internal symmetry and not the space-time symmetry. Okay, so these are the conditions. So I wanted to make sure that this like legal document, I want to make sure that what I'm talking about, and then I'm going to show that there is no such thing that satisfies all these conditions. Okay. So actually, Daniel and I wrote a 150-page paper on this subject, so I cannot tell you everything about it, but I want to explain our idea. And the main idea, and since there are some quantum information and condensed matter people here, I wanted to note that the main idea is actually the relation between holography of quantum gravity and quantum error correcting code in quantum information theory. The relation between these notions has been very important in development of holography for the last 10 years or so. So the correspondence is very sort of interesting. So in the case of ADS-CFT correspondence, there are some conformal field theory local state, and that corresponds to ADS local state. And when the gravity approximation is good, there are some subset of states described by local operators that describe some geometric state in the gravitational theory. In the quantum error correcting code, there are physical qubit and logical qubit. And the correspondence, so this is to encode information about the logical qubit in the tensor product of Hilbert space, making up physical qubit. And the way that the holography works is very much in parallel to this construction of quantum error correcting code. That is that in the weakly coupled gravitational descriptions, there are local excitation in the gravitational series. And those are encoded in the conformal field theory data exactly in a way that this quantum error correcting code works. So that was the insight. And for example, this famous happy code sort of illustrates how this works. That the local excitation within a gravity can be described by some kind of entanglement between data on the boundary. Okay, so in the quantum information theory, there is a very famous theorem called the Easton-Knill theorem that forbids quantum error correcting code to have continuous symmetry which acts transversely on a physical qubit. Namely that this kind of operation does not couple physical subsystem within the same code block. So what this means is that there is no way to construct, if I understand it correctly, this quantum error correcting code in such a way that the action of the group on the physical qubit that act individually on each of these physical qubits is compatible with action of the same group on the logical qubit. Now, namely that there are no error correcting codes that are preserved under this kind of G action. So that's a sort of a statement of Easton-Knill theorem. So when Daniel and I were actually writing paper, I didn't know this theorem, but I learned after the fact. And we realized that this is actually exactly what we are using. Namely, that this kind of transversality is implied by Noether theorem. So, for example, therefore, for symmetries that satisfy the generalized Noether theorem, namely split property, cannot be compatible with this holographic correspondence. So that's the idea of the proof. So the proof goes like if the gravitational theory has global symmetry, there must be a bulk local operator that transforms faithfully into another local operator. And so in that case, there is this, suppose you have this charged operator in the middle of ABS, and suppose you try to add some symmetry operator. Now, symmetry operator can be decomposed into, so suppose you decompose a boundary into a set of open sets with some boundary between them. Then we can write this operator as product of operator and possibly some additional operator that takes care of the transformation at the boundary between these subsets. And there is some subtlety in this construction because so one can easily see that by this entanglement wedge reconstruction, the operator constructed here acting on this region can only act non-trivially in this part of the bulk space. So therefore, each one of them actually commute with X. Now I need to argue that this H commute with this, but this operator would act only non-trivially on these edges. So it's reasonable to assume that that also commute with X. And then that would be contradiction. But you might worry that, well, this is a little bit flaky. So actually there is another construction that we can avoid this problem altogether. So suppose you have this bulk geometry which has various so non-trivial set of boundaries, so this joint boundary. So if we have such construction, then you can actually have this structure where a symmetry operator is a product of operator acting on each boundary regions. And so we can avoid the subtlety by existence of a boundary of this open set and the edge operator altogether. But main point I would like to say is that therefore, if a gravitational theory has global symmetry, there must be a bulk operator that transforms faithfully into each other, like this operator that I placed over here. And I want to say that that's inconsistent because such bulk operator must transform faithfully into another local operator under symmetry action. However, if Noether theorem is satisfied, then this symmetry, the operators that implement a symmetry must be decomposable in this way, and each one of these elements decomposition commute with the bulk local operator. So therefore, the operator commute with the bulk operator entirely, so it's contradiction. Okay? So this shows that there cannot be global symmetry satisfied the conditions that I have listed. Any question? Okay, is that clear?
But I'm trying to ask at the very beginning, let's say that we will use the general relativity as a theory in the flat space, and just tensor field in the flat space, right? Then it looks like this normal local field theory, right? This commutator. Of course, I understand that the light code would be different in the real world than this coordinates we started from. So the flat space is unobservable, right? But I'm using it as a theoretical device because to compare with the normal quantum field theory.
So?
And then I do not see what's the difference.
I'm going to show you that so in the corresponding, so I'm not going to talk about flat space, but in ATS, in the corresponding setup, you can find an example where low energy theory looks as consistent as you just described, but nevertheless does not have UV completion. Okay, so I'll give you an example. If you let me finish until the end, I'll give you an example. Okay, so I have a few comments about this derivation. Okay, so I showed that the symmetry operator, which have this generalized Noether theorem property that it can be decomposed into this product of unitary operator, has to commute with the local operator in the gravitational theory, so therefore that was contradiction. And so I don't have time to explain, but this argument works also for spontaneously broken global symmetry. So this is of interest because suppose you have low energy effective theory which has shift symmetry, exact shift symmetry, then that would be the, a spontaneously broken situation. So this theorem would then mean that this shift symmetry has to be broken in some way, that you cannot have infinitely long flat direction. This argument generalized to p-form symmetry and also symmetry with 't-Hooft anomaly. But the situation with non-invertible symmetry is subtle, so this is the question of whether non-invertible symmetry is splittable or not, and I had some interesting discussion with Shahen earlier this week. This argument does not work for 2D gravity, and in fact there are counterexamples. There are many string Walsh's theories that you can think of as describing 2D gravity, but that has global symmetry. For example, heterotic string Walsh's theory has E8 cross E8 or SO32 global symmetry, which becomes space-time symmetry in the string theory. So these are counterexamples, and also 3D-oriented pure Einstein gravity is not applicable. And I think that general rule seems to be that your gravitational theory has to be interesting enough to contain black holes. So if the theory contains black holes, I think this is applicable. But for 2D gravity on the worldsheet, you don't have black holes, so that may be the reason.
Sure. And for the second point, in 2 + 1 dimensions, if you have a one-form symmetry with a 't-Hooft anomaly, the topological operator cannot be open, for instance, in Chern-Simons series. So at least they are not endable.
I think so. So this is an example where the one-form global symmetries. Yeah. So in general topology, no. But I'm talking about the flat space. So.
But it's really the fact that if you have a one-form symmetry with an anomaly, it means that you have two lines of the symmetry.
Yeah, I know that example, but I think that for flat space there is no. So you have to have non-trivial topology in space-time in order to actually to cause non-splittability. We can talk about this. This is an interesting example. So, however, I can easily imagine Arcad is not satisfied with this as a counterexample because this does not provide useful constraint. That low energy gravity theory cannot have global symmetry, but so what? Because there might be some accidental symmetry that can be broken in high energy, or can be gauged in high energy, right? So it would be nice to be able to sort of give some constraint. Of how this is broken. In fact, there is actually approximate version of Eastern Cunil theorem. So since there are many people who are knowledgeable about quantum information theory, actually I would be very happy. I will be here for 1 more week, and so I'd be happy to have discussion on this subject. And this actually, this work seems to be very interesting because this approximate version of the Eastern Cunil theorem seems to say that error is bounded by inverse power of qubit size, which seems to be exactly the corresponding expectation that the global symmetry can be violated by inverse power of the power of Newton coupling. And so there is a question of whether you can in general bound the size of breaking, whether it is perturbative like power of G Newton, or non-perturbative like exponential of inverse of G Newton. And this general approximate version of Eastern Cunil theorem seems to say that it's power. So I think that's very interesting. I want to understand this better. And so that's why what I meant by we may be able to use it to bound the quantum gravity violation in global symmetry. So if there are people interested in discussing this, I'm very, very happy to do that. So there is another thing called the completeness of gauge charge, which states that every finite dimensional unitary representation of long-range gauge symmetry must be realized, that all possible charge should appear in some sense. But however, this again is not very useful by itself because we do not know whether mass of lightest charged particle can be bounded above. And so if there is such a bound, then we can say that, well, if the low energy effective theory does not satisfy this condition, then it's in Swampland. But if you can have arbitrary, this required particle can have arbitrary large mass, then we cannot exclude low energy effective theory. So this by itself is not useful. So this leads to some idea called weak gravity conjecture. And so unfortunately, I do not have much time to discuss this. I only have maybe 25 minutes or so. But this actually quantifies this kind of absence of global symmetry and completeness by saying that in any low energy theory described by Einstein gravity and Maxwell theory and finite number matter fields, if it has UV completion as consistent quantum theory, there must be a particle of charge Q and mass M, much smaller than Planck scale, such that this inequality holds. Okay. So this is actually very useful for constraint. And in fact, Kumran and I wrote some speculative paper about 9 years ago, saying that if you strengthen this condition a little bit, then in fact we can derive inequality between the amount of dark energy in the universe and the sum of neutrino masses. And these numbers turn out to be very close to each other. And so this can potentially explain it. But this is one of my most speculative paper on, that I have written. So let me move on. So there is this. We have covered the first set of this non-Wilsonian statement. So let me move on to the second set, the absence of adjustable parameters. So I think, as far as I know, this is the oldest Swampland conjecture. If there are other candidates, I would like to know. Maybe some Greek philosopher might have had some speculation about the Swampland conjecture. But so this is Albert Einstein's autobiographical note. This is actually very interesting reading. And there's a chapter in this book where he discussed the notion of natural unit, that you set h bar and g Newton and speed of light to be equal to 1. So then if you do that, he says that the only dimensionless constant could occur in the basic equation of physics. However, for such parameters, he says, concerning such, I would like to state a theorem which at present cannot be based upon anything more than upon faith in the simplicity, namely intelligibility of nature, that there are no adjustable constant of this kind. So more modern way of saying it, which I stated with Kumran in 2006 as a sort of zeroth version of distance conjecture, is that every parameter in quantum gravity must be an expectation value of a dynamical field. So for each parameter, there must be a dynamical field, and it can be varied by changing its expectation value. So that's sort of conjecture zero. In fact, we can actually prove this, and so I made this remark in my concluding remark at string 2022. I haven't written it for a reason I will explain later. But let's try to prove this statement that there is always, for each parameter, there is always a field in the bulk whose expectation value determines. This is actually a very easy proof. So suppose you have a gravitational theory with continuous parameter lambda. Okay, so suppose you have such family of theories. Then there must be a corresponding parameter in conformal field theory. So you can consider varying that parameter. But we know in conformal field theory what happens if you vary the parameter. Well, there must be exactly marginal operator, which generates this variation. Well, actually, to be precise, so this is why I haven't written it. This is existence of exactly marginal operator for every continuous parameter is a conjecture about conformal field theory and requires proof. And in fact, I'm working with Shota Komatsu, Yuya Kusuki, and Marco Maineri, and we actually almost completed the proof, and so but we are still sort of tying up some detail. So this is actually something we can in principle prove, and so assuming this, then you can say that if there is an exactly marginal operator in conformal field theory, by the dictionary of ADS-shaped correspondence, there must be a massless scalar field, such that its expectation value corresponds to the parameter. So this is the proof. Okay, so or in a more modern parlance, we can say that the absence of adjustable parameter in quantum gravity is equivalent to absence of -1 form symmetry, and in ADS-CFT correspondence, it can be proven by the existence of exactly marginal operator to generate the deformation. Namely, we can say that the statement that I'm trying to prove with Shota, Yuya, and Marco is actually the splittability of -1 form symmetry in conformal field theory. So this is very interesting because these two lines of non-Wilsonian statement, absence of adjustable parameter and absence of global symmetry, are actually seems to be unified, that they have a similar origin. But again, Arkady might complain that this is not very useful because what appear to be adjustable parameter in low energy theory may be fixed by potential in more fundamental theory, and they are not really adjustable from low energy point of view. So for example, the standard model of particle physics has 19 parameters, or even more if you include the parameters that it requires for neutrino masses. And the lambda CDM model has 6 parameters. But not many people argue that standard model of particle physics is in Swampland. Some people argue that lambda CDM model is in Swampland, but for different reasons. And so they don't contain dynamical field corresponding to these parameters. And but we don't regard standard model as. So what's most likely to happen is that there is more fundamental theory where these parameters can be expectation value of some unknown field, but there is a potential for these fields that are fixed. And so therefore in low energy they look like parameter. Okay? Even though there is no corresponding field. But does not contradict with this line of argument. So how can you make this more useful? So when Kumran and I wrote this paper, we didn't stop therefore at this conjecture 0. We studied many examples on the string theory based construction and came up with additional common features. One is that on this parameter space, if it is non-empty, then there is always an infinite distance direction. And so typically it goes like this kind of funnel. So one example is that if you compactify string theory on Calabi-Yau manifold, the volume of Calabi-Yau will become large, and that's going to be the infinite distance direction. And as you go to this infinite distance, the low energy effective theory is always broken if you go sufficiently far in that direction. And it's broken by the emergence of tower of light particle. So that seems to be a common feature of all known construction. So we formulated this in this way, conjecture 0, 1, 2. So conjecture 0 is that basically every parameter is the expectation value of dynamical field. But then we say that choose any point in the moduli space of gravitational theory. For any positive number, there is always another point which is distance away from that number. And if you go to that direction, then there is a tower of light particle whose mass goes like exponential of e to the minus alpha, where alpha is some parameter. Okay, so we wanted to actually provide a constraint on alpha, but in math paper, we only said that alpha is order 1 in Planck scale. So what I would like to do is actually to put some bound on these parameters. That will come later in the next 15 minutes. But I just wanted to point out some amusing things. So we wrote this paper in 2006. And for the first 10 years or so, it remains a very sad paper. So like that, actually, Slack Inspires has X account. And occasionally, they actually post some notice when there is an interesting citation phenomena. So they actually point out that this paper is a very sad one. For example, I think this year there was 0 citation. It's very sad. But then suddenly it shot up. And so they posted this when this paper reached 1,000 citation. And then called this paper is Sleeping Beauty. So the question is that who woke up? Who woke her up? Okay, who woke up? So, okay, so does anybody remember what happened around 2014 or 15? So the BICEP announced that the tensor scalar ratio of the cosmic microwave radiation, if it has a primordial origin, it would have contradicted the distance conjecture. That's not what they proposed. That if this was the case, then it would have been the evidence for inflation. But in fact, yeah. So when this happened, actually, I was deputy dean of physical science at Caltech, and I was working in the dean's office, and then the dean came in and said that was about a month before this announcement was made, and he said, "You know, the BICEP is going to make an announcement." I asked what R is, and he said 0.2. And they said, "Great, it's going to kill string theory." And the reason I said that is that if you make actually reasonable assumption about this alpha in this distance conjecture, then you can actually put some kind of bound on the tensor scalar ratio. And this is actually rather generous bound. But even for this generous bound, if you combine that with Rice bound, then 0.2, anything beyond 0.2 will be inconsistent. So that's what I said. The dean didn't listen to me, and he still remembers that, of course. He teases me about it. I think it's interesting. Therefore, so now actually Planck. I think the next generation of Shinbi experiment would go further down. So I think it would be interesting to actually quantify alpha more precisely and see how we can actually lower this blue line. Okay, so that's what I would like to understand. I cannot do this yet in inflation era, but we can try doing this for anti-data space. So anyway, so the thing I wanted to do was that these two conjectures have been tested for the last since 2006 for 18 years, I think, no, 19 years. This conjecture has been tested in many examples in string theory, and no counterexample, as far as I know, has been found. And if alpha can be bounded, it will be very useful for a variety of reasons, including this. And so this actually was formulated in the context of ADS-CFT correspondence by Eric Perlmutter and collaborators. And instead of mass, here we consider conformal dimension of operators. And the moduli space in gravitational theory, of course, correspond to the conformal manifold. So this is actually the work that I did with Yifan Wang last year. And actually proving this, part of this in the simpler context of ADS3 and CFT2. And what actually I would like to mention here in particular is that we were able to, in this context, bound alpha both from above and below. So alpha is bounded in the corresponding conformal field theory between 1 and 1 over square root of central charge. So basically this is what Yifan and I did that. So if there is a point in conformal manifold where the conformal dimension of some operator vanishes, then the approach to that direction that point is actually infinite direction from interior of the conformal manifold. And the approach to that is exponential in that conformal dimension. Weight, and then this exponent is bounded from both above and below. Okay? So if you translate that in the language of ADS gravity, then we can actually translate this bound in the ADS scale and Planck scale. So in particular, if you have actually turned out to have a family of gravitational theory which becomes flat space, then this becomes infinite, but this remains finite, and then this is bound alpha by Planck scale. So suppose this is actually 1. Then actually you can actually, this is actually, alpha is like 1/10 of Planck scale, so you can actually lower this at least order of magnitude, if corresponding thing is true in flat space gravity.
Sorry, I suppose that this conjecture is not supposed to be true for minimal models.
Oh yeah, because there is no moduli space. This assumes existence of moduli space, and you can see that in order for moduli, so this already shows that in order for the moduli space is infinite direction to exist, she has to be greater than 1 or equal to 1, because otherwise this inequality is inconsistent. So this is consistent with the expectation that she has to be equal or greater than 1 in order to have a non-trivial moduli space. Okay, so that's consistent. Unitarity is important. We use unitarity, as I'm going to explain. So so I have still maybe 10 minutes. Yeah. So let me actually explain the idea of that leads to the proof of this claim. Okay, so let's consider simplest case when there is only one exactly marginal operator. The moduli space is one-dimensional. If we understand it, then generalizing to a higher dimensional moduli space is easy. So suppose there is a primary field whose conformal dimension vanishes at some point on the conformal manifold. So choose the geodesic that goes to that point. Then a renormalization group equation tells you that the conformal dimension satisfies this equation, where the variation of the conformal dimension with respect to the parameter of CFT is given by the 3-point function of that operator with exactly marginal operator. So this is a equation you can derive. And so that means that if in the limit when you approaches to the point where conformal dimension vanishes, this 3-point function vanishes at least linearly, then there is a logarithmic divergence of the difference by integrating this equation. So you want to show that the 3-point function vanishes at least linearly toward that point. In fact, Yifan and I were able to prove stronger statement that it not only vanishes linearly, but coefficient is 1. So then by integrating this equation, you can show that conformal dimension goes like exponential of minus t. So in this case, it happens that if there is only one exactly marginal operator, then alpha is actually 1. Okay. So let me give a proof of that. So we're going to use the following fact that since you have a global conformal symmetry, you can prove that if you take the derivative of this operator whose conformal dimension vanishes, then there is an operator j with some additional square root, where j is normalized so that 2-point function is equal to 1. So therefore, you can show that with respect to j, m, 3-point function is jj bar m, and we want to show that jj bar m, 3-point function, is 1. So how do we prove this? So actually, this is proven by a conformal bootstrap. So by using crossing symmetry. So in view of time, I'm going to just give you the simple but less rigorous proof. So in the paper, I give more rigorous proof, but let me just illustrate how the proof goes. So the idea is the following. So suppose 2-point function of original operator with conformal dimension delta is normalized to be 1. So if we define derivative of O to be square root of delta times j, then if you take derivative of this, you get deltas, but that's cancelled by this square root factor, so it's 1. And then similarly, jj bar, and j bar 2-point function is delta. So I transcribe this over here. And so therefore, in T channel, you have Z, D, and W, U. So this is 1. And then there are contribution of other operators. In the S channel, you have this one and this one. So then you get the delta square from here. And then the next one is where you have exactly marginal operator in between here, which gives you square with a 3-point function. So I was very happy when I realized that. So these are actually the conformal block for this global conformal block in this particular case, and these are actually same function, and this vanishes in the limit, and you can show that others have different function form and they are orthogonal to this. So therefore, by crossing symmetry, it has to be that this is equal to 1. Now, proving that this dot 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 here and dot 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 here are orthogonal to each other requires a little bit of work. So I'm going to skip it. But with this, you can prove this. Okay. So if you have more than one marginal operator, this is a simple generalization. So instead of, so here I consider the insertion of marginal operator. So you have this term. If you have more than one marginal operator, you have more operator you can insert here. So instead of one term, you have some of these terms, which actually potentially reduce the amount of alpha, and so alpha can be less than equal to 1. That's the proof of the upper bound. The lower bound can be proven in a somewhat similar way. So in view of time, I'm going to skip that. So what I wanted to say was that we have this kind of two lines of a non-Wilsonian statement. And I hope you agree that at least this type of condition is non-trivial, because what this means is that if you have low energy effective theory with a flat scalar field with flat potential, which never develop light particle, even if it goes scalar field expectation value changes beyond Planck scale, such theory should be in Swampland. Okay, so this will be a sort of very sharp condition, albeit weak, but possibly weak, but sharp condition on low energy effective theory. Okay, so I just pointed out that actually there is actually a close relation between the absence of adjustable parameter and the absence of global symmetry. Both has to do with splittability of symmetry. So the absence of global symmetry is closely related to splittability and the existence of Noether theorem for global symmetry. And the absence of adjustable parameter is related to splittability of -1 form symmetry. So these seems to be closely related, at least in the context of ADS-CFT correspondence. So it would be nice to actually, so now that we are interested in partially succeeding in quantifying distance conjecture and weak gravity conjecture, it would be interesting to find out whether there are also relations between these strengthened version or quantified version of conjecture. So there are various interesting directions. As I said, the approximate version of Easton-Knudsen theorem can be useful in this context. And I would like to generalize this to higher dimensional conformal theory also. So that would be an obvious direction to explore. So summary is gravity is different, but I would like to say a few more words. So I think I have demonstrated for you that there are constraints on low energy effective theory of gravitational system that cannot be captured by the standard Wilsonian paradigm. So there are two lines of non-Wilsonian statement. And in ADS-CFT, we can quantify and prove part of the conjecture. So I'm working to strengthen these results and generalize them for space-time with zero and positive vacuum energy. So that can be even more useful. Okay, thank you very much for listening to me.
You mentioned that in the distance picture you have this infinite tower of light states. Is this something that string theory also predicts for you as well? Like, is there a mechanism that
So string theory, all non-construction string theory has this feature. So we don't have a definition of string theory. So we cannot prove this from the first principle except from ADS-CFT. But in all non-Calabi-Yau compactification, this is true. So people like Timo Weigand studied this in many, many examples, and Wolfgang Lerche and Dieter Lust, and so no counterexample have been found, as far as I know. It's not like string theory doesn't have yet first principle definition. There are constructions, based on Calabi-Yau compactification and the variations. So we only can look up all these examples. So you might say, well, you are only looking at some small lampposts, but in all the lampposts, we can search these holes.
Another question. I don't see any immediate questions. I think we take a 10-minute break maybe, and then we continue to the next talk. And thank you also.
Thank you.